Welcome to the lesson on electronic navigation aids. The average yacht or motorboat these days has an array of electronic navigational equipment at its disposal. These are usually fully integrated and are able to provide a wealth of information to assist your navigation. It must be stressed, however, that you should not rely entirely on electronic navigation aids and must double-check any information by traditional means whenever possible. Keeping a regular plot of your position on your chart and a written record of your course and log reading in the vessel's logbook will give you an accurate starting position to draw an estimated position if your electronic navigation systems should fail. The fundamental sensors that make up any vessel's instrument system include the log, which measures the vessel's speed and distance, depth sounder, wind speed and direction. Most boats will also carry some form of global positioning system, GPS, to plot their position. A chart plotter to show the vessel's position, identified via GPS, may also be fitted. Or an iPad or smartphone with a nautical charting app may be used. Increasingly, leisure boats are also now fitted with radar for navigation or vessel tracking, and this can be displayed on a separate screen or via the chart plotter or multifunction display. Automatic Identification System, or AIS, may also be installed, and this uses the chart plotter screen or sometimes a standalone unit to visually represent the position and movement of other vessels in your vicinity. Let's now take a look at each of these in turn. As you learned in the lesson on estimated position, aside from the steering compass, the ship's log, which measures speed and the distance you have sailed through the water, is the most basic tool for establishing position if everything else fails. However, it is useless unless properly calibrated, and in particular, a log which underreads can lead you into danger, for instance by giving the impression that you are further away from an approaching navigational hazard than you actually are. We see here that an underreading log, when used to calculate our position, would lead us to believe we were further south of the island than we actually were. If we were relying on the log for calculating our position, this is obviously going to be a problem. And if we were using the log to estimate our progress towards a tidal gate, we might find ourselves arriving either too early or too late. Of course, as a prudent skipper, you would be keeping an eye on other information sources and would have noticed the depth dropping as you approached the shallowing seabed around the island and would have concluded that the log was misbehaving. To calibrate your log, find two charted features and make two runs between them under power in opposite directions when the tidal stream is slack. Note the distance for each run from your log, add them together, and divide by 2 to get the average. You then compare your log reading with the charted distance, and any difference is the error on the log. If the log can be adjusted, you make the necessary adjustments and then recheck it. If it cannot be adjusted, you make a note of the error and allow for it in your calculations. In this example, we zero our trip reading as we navigate north past Mutton East Cardinal and record our log reading of 0.96 as we passed East Powell Cardinal. Then we turn around and go back, recording our log reading of 0.99 as we repass East Powell and 2.02 when we arrive back at Mutton East. This gives a total on the log of 1.99 miles. Since the total charted distance there and back is 1.84 miles, Simple arithmetic tells us that our log is overreading by 8.15%. Most logs are adjusted relative to a baseline of 1. So in this case, if you wanted to adjust your log, you would need to adjust the baseline to 0.924, which is the charted distance divided by the log reading. Modern logs linked to GPS receivers might also be automatically calibrated by entering Setup mode and pushing a button to set the boat speed through the water to equal her speed over the ground at that instant. But of course, this only works if there's no tidal stream. Carefully check your own log's instruction manual when making changes to calibration. You should also regularly inspect your log's impeller, which is the small paddle wheel sticking out through a hole in the bottom of the boat that actually measures your progress through the water. Check that the paddle wheel is not fouled and thus reading incorrectly. Just make sure that you've got a bung to hand, or you'll end up with a very wet boat. You will remember from the lesson on tidal heights that the depth of water under your boat is measured with an echo or depth sounder. An electronic depth sounder sends out ultrasonic signals via a transducer towards the seabed and measures the time taken for the sound signals to be reflected back to calculate the depth. The transducer is situated below the waterline and should be calibrated to take account of the offset to give the correct depth. The measured depth can be given as either from below the keel or from the waterline, which is most often the case. Make sure that you know if and how it's calibrated, and check it regularly with the lead line, which you should carry anyway as a backup. Which method you choose is up to you. Depth of water is useful because it agrees with the depth you might calculate from charted depth plus height of tide, and it's also helpful when you're anchoring, because you just need to multiply the depth of water by 4, assuming you're using all chain, to calculate how much chain to let out. Whereas if you set it to read clearance under your keel, you will know exactly how much you've got to spare if you are navigating in shallow water. And if you're at anchor or on a mooring, and you're trying to work out whether you'll ground at low water, all you need to do is subtract the fall from your depth sounder reading. Many charter companies calibrate their sounders to depth below keel in order to show novice sailors how close they are to running aground. To check the accuracy of your depth sounder, anchor where you are confident that the bottom is relatively flat, and use a lead line to measure the exact depth of water abeam the depth sounder's transducer position on both sides of the vessel. Average the two measurements and compare the average with the reading on your depth sounder. If it's supposed to be displaying the depth of water, then the two should be the same. If it's supposed to be reading the clearance under your keel, subtract your draft from the average on the lead line, and the result should equal the displayed depth. If the numbers don't add up, you've got to adjust the offset, programmed into your depth sounder. If you wish it to read depth of water, then the offset is calculated as average depth on the lead line minus the reading on the depth sounder. So, in this example, if the port side lead line measured 2.08 meters and the starboard side 2.20, then the average will be 2.14 meters. And with the depth sounder reading of 1.75 meters, you would need to set the offset to plus 0.39 meters. If you want your depth sounder to read clearance under your keel, the offset is calculated as average depth on the lead line minus your draft minus the reading on your depth sounder. Therefore, with an average on the lead line of 2.14 meters, a draft of 1.6 meters, and a depth sounder reading of 1.75 meters, The offset would be 2.14 minus 1.6 minus 1.75, which equals minus 1.21 meters. You could also stop your vessel close to a tidal gauge and confirm your depth sounder reading against the tidal gauge reading, making any necessary adjustments if your sounder is reading clearance under the keel. Your echo sounder reading can, however, be subject to several factors that might cause it to give a false or no depth reading. These include the composition of the seabed, air bubbles caused by another vessel's wake, water salinity, currents, calibration errors, sediment suspension, and temperature layers. Or possibly even objects floating beneath the surface. And when you're going astern, a mass of air bubbles will be created under the vessel's hull. These air bubbles are good reflectors of sound, and the depth sounder may show a much shallower depth rather than a genuine reading, and occasionally no depth reading will be displayed until the water becomes less turbulent, which can be a little disconcerting if you're reversing your vessel onto a quay with a limited depth clearance. Depth sounders can also be set to alert you with deep and shallow alarms. You might choose to set your shallow alarm to sound if your depth falls below a safety threshold, whereas the deep alarm can provide a warning if your anchor is dragging and you're being carried away into deeper water. Most vessels are equipped with wind instruments that can display the wind strength, normally in knots, and the wind angle relative to your vessel, measured by an anemometer at the masthead or highest point. In their simplest form, they read what's known as apparent wind speed. In other words, the wind including that resulting from the vessel's own motion. If you stuck your head out the window of a moving car, you would experience apparent wind. That is, wind induced by forward motion. The wind direction is displayed relative to the vessel's heading. More sophisticated systems, linked to the vessel's electronic log, can be set to display the true wind direction and speed. In this example, a boat sailing at 5 knots with 10 knots of wind on the port beam would see an apparent wind direction of approximately 60 degrees and an apparent wind speed of 11.2 knots, as shown on the right-hand display. Whereas, if her wind instrument were interfaced into her log and set to read true wind speed and direction, then it would read 90 degrees and 10 knots, as shown on the left-hand display. A bit like whether you choose to set your depth sounder to read depth of water or clearance under your keel, whether you choose apparent or true is up to you. However, by selecting true, you get a much better idea of the real conditions, which can be extremely valuable, especially if you're running downwind in a strong wind, when you might otherwise be lulled into believing that it is considerably less windy than it really is. Some boats will have 2 displays, allowing true and apparent wind to be displayed at the same time. Obviously, true wind speed and direction can only be accurately calculated if both the log and the vessel's anemometer, which is the little propeller at the top of her mast that measures the wind speed, are both properly calibrated. Now let's look at GPS, or as you will probably know it, Global Positioning System. In fact, GPS has become the generic term, but is just one system within what's properly called the Global Navigation Satellite System, abbreviated to GNSS. Navstar GPS is the US Navy's global satellite positioning system, which since the mid-1990s has been opened up for civilian use around the world, and until recently was the predominant system in use. Other satellite systems within the GNSS include the Russian GLONASS, the European Union's Galileo, and China's Beidou. GNSS-compatible equipment can use navigational satellites from other networks beyond the Navstar GPS system. All GNSS receivers are compatible with GPS, but not all GPS receivers are necessarily compatible with all of the GNSS constellations. GNSS is the correct term, but we will use GPS generically when looking at satellite-derived positions, as this is the term in common usage. Navstar GPS is based on a constellation of 24 satellites orbiting the Earth which act as reference points. GPS works in any weather conditions, anywhere in the world, 24 hours a day, with no subscription fees or setup charges. The other global navigation satellite systems operate in a similar fashion. Your onboard GPS receiver determines your position by measuring the time it takes signals transmitted from these satellites to reach the receiver. Each satellite within a constellation continuously transmits its own position and a time signal. Your onboard receiver calculates the time taken for this transmitted signal to arrive and how far the satellite is from the vessel. This distance range gives a circle of position on the Earth's surface, and thus your position must be somewhere along this line. Using the data from more than one satellite will give a number of spherical position lines, and your vessel will be positioned where these lines intersect, just as it would be when you take a 3-point fix with your hand-bearing compass. And, just like that 3-point fix with your hand-bearing compass, a fix obtained by just 3 satellites will produce an area of uncertainty, or cocked hat. With more than 4 satellites, we can begin to have confidence in the accuracy of the fix. Up to 12 GPS satellites should be available to view above the horizon at any time, and as accuracy increases still further with more fixes, it is possible to obtain a position which is accurate to within 10 meters 95% of the time. This GPS unit is showing how the position is being fixed by reference to 12 satellites out of 24, which are visible to it, in other words, above the horizon. The 10-meter accuracy of GPS can be improved to better than 3 meters by means of satellite-based augmentation systems. The American Wide Area Augmentation System, WAAS, and European Geostationary Navigation Overlay Service, EGNOS, are 2 such systems. Other regional systems are also in operation. Satellite-based augmentation systems correct GPS signal errors caused by ionospheric disturbances, timing and satellite orbit errors, and also provide integrity information on each satellite. Multiple fixed ground stations monitor GPS satellite data, and as they know their own position, they can calculate the reliability and accuracy of the received positioning data and then transmit another differential signal via geostationary satellites to your GPS receiver. Differential Global Positioning System is a similar augmentation service that uses marine radio beacons to broadcast accuracy improvements. However, this service is now being discontinued in favor of satellite-based augmentation systems. Neither type of augmentation is globally available at present. Another source of possible position error is the angle of intersection of the position spheres. As with a 3-point compass fix, it's important that the position lines are well spread to prevent shallow angles of intersection and large areas of imprecision. In this example, the satellites are poorly positioned, giving shallow angles of intersection on the position lines. Well-spread satellites give a much better angle of intersection. When the ranged spheres from the visible satellites intersect at very shallow angles, this creates what is known as horizontal dilution of precision, or HDOP. The fixed position will lie somewhere in the area where the two spheres intersect. When the satellite's ranges intersect at right angles, the possible fix area is as small as it can be, creating an optimum area of precision. Your GPS receiver will display the HDOP number from the available satellites. The higher the HDOP number, the less precise the position fix will be. An HDOP of 2 or less is excellent, and higher than 4 is considered unreliable for safe navigation by the International Maritime Organization. Many GPS receivers will reject a fix offered with an HDOP higher than 5 and will return a lost fix message. In this display, we see that the quality of the position fix is poor. The HDOP is 14.3 and position accuracy is a pretty woeful 153 meters. Turning augmentation to on would enable the use of a differential signal, such as WAAS or EGNOS, to refine the accuracy of the position. The system is reporting that GPS, Galileo, GLONASS, and Beidou satellites are available. However, the use of multiple GNSS systems does not necessarily mean improved position accuracy, but does increase the ability to obtain a fix when one system has an issue or where a limited sky view is available for any one system. You also need to ensure that your GPS antenna is correctly sited. Many GPS receivers and chart plotters have an inbuilt antenna, which is fine if they're located outside on a motor yacht's flybridge or at the helm of a sailing vessel, but not so good if they're down below at the chart table. So if this is the case, it's well worth investing in an external antenna. And contrary to what you might think, this needs to be installed relatively low down on your vessel to minimize errors attributable to the very weak GPS signals bouncing off the sea surface and the effect of the vessel pitching and rolling in big waves. Be aware, though, that any GPS antenna located on the boat's push pit is ideally sited for people grabbing onto it or knocking it off the vertical and thus degrading its performance. The GPS antenna should also be sited either above or below the radar antenna, and ideally at least 1 meter away from the VHF aerial to avoid interference. The antenna should have a clear view of the sky and not be shielded in any way. In this image, we see that the chart plotter is utilizing the inbuilt GPS antenna, and the quality of the position fix is poor. Switching to an external antenna, if available, would result in the possibility of sighting more satellites and would improve the quality of the fix. In its simplest form, a GPS receiver will give you a latitude and longitude position displayed on a screen. By keeping a record of the vessel's positions over a period of time, the GPS receiver can then calculate the vessel's speed and the course it has made good in the time between positions. We will look at that in more detail shortly. A chart plotter uses this satellite-derived location to visually represent your position on an electronic chart. Here we see the vessel's position represented on the chart plotter by the black vessel icon, and the latitude and longitude position is shown in the top left-hand corner of the chart plotter. Whereas the standalone GPS unit is showing the vessel's position as latitude and longitude coordinates, which we could then use to plot the vessel's position onto our paper chart. GPS has revolutionized navigation. However, the apparently very accurate positions obtained from GPS can lead to over-reliance. It should be treated as an aid to navigation, and not the only method of position fixing. To use it effectively, the navigator must learn about the limitations of the equipment and the simple checks that must be performed to ensure the GPS information is not leading you into danger. Basic GPS functions do not predict the vessel's future position, take account of tidal streams, or indicate proximity to hazards. Your instructor has sailed down the Little Russell Channel towards St. Peter Port in the Channel Islands, with his GPS and chart plotter telling him that he was 1 mile inland. Fortunately, it was the other way around. Chart plotters superbly portray the vessel's position for general navigation, but when entering harbours they may be giving a false sense of security. I would be much more confident in fixing my position by looking out the side of the boat and seeing us approaching or passing a buoy. Imagine if the plotter had been telling me that I was perfectly safe as I headed straight for the rocks. That's pretty much exactly what happened here. The accident report makes sobering reading. And as we learned in the chart work lesson, GPS positions can be more accurate than chart surveys, giving us an impression of position certainty that is not always the case. Look at the top of Training Chart 4. The Source Data panel tells us that Area G was surveyed by Leadline between 1905 and 1918. Area G corresponds with November Bay in the detail chartlet B of Training Chart 4. So, whilst your GPS and chart plotter might be giving you a seemingly very accurate display of your position, you should treat this with some caution. If we look at the pilotage notes for this area in the Training Almanac, we see that the charted contours are approximated and considered unreliable, so you should navigate with extreme caution. Pilotage and local knowledge would aid any entrance, particularly at night, as there are limited lit navigational aids. So the point to remember is to avoid over-reliance on your GPS for navigation, and make sure you inspect your chart and read the almanac or pilot book to assess the implications of any limitations. And remember to check that your GPS and the chart you're using are working to the same datum, usually WGS84. We also looked at that in the lesson on chart work. The dangers of sailing in an area of navigational hazards while relying solely on a navigation system which is reliant on electrical power should be self-evident. On board your vessel, the GPS aerial is vulnerable to storm damage and water ingress. Electrical connections might fail, your batteries might go flat, or the GPS receiver itself might develop a fault. Of course, you could carry a battery-powered backup. However, there are also rare circumstances when the accuracy of GPS fixes degrades below the level necessary for safe navigation. And occasionally, national, military, and defense agencies conduct exercises and tests on military systems which may result in the denial of GPS service to civilian users for short periods. These are usually widely publicized and are not normally held in areas of dense usage. However, it shouldn't be assumed that any loss of service is due to jamming exercises. There are, of course, so many different GPS receiver models available that it would be unrealistic for me to give instructions on which buttons to push to get which bit of information from your GPS or any other instruments. It's up to you to self-educate on whichever equipment you have aboard. But you should take the time to get to know whatever equipment you are using and don't rely on it until you fully understand what it can and cannot do. Let's have a look now at some of what our GPS receivers can do for us. It can give us our position in two ways, either by latitude and longitude or by bearing and distance to a specified waypoint. We can plot the GPS-derived latitude and longitude position onto our chart. And we can also plot our position relative to a waypoint. Waypoints are latitude and longitude coordinates selected by you on the chart or provided in almanacs and sailing directions. They can be used to identify the beginning or end of a passage, to mark successive legs on a route, or to guide you through an area of hazards. The waypoint's latitude and longitude coordinates are entered by you and stored in a list on the GPS unit's memory to be used as navigational reference points. If you're using waypoints supplied from an almanac, sailing directions, or other reference source, always plot it on your chart first to check its position is correct before entering it into your GPS or chart plotter. And if you're setting your own waypoints, check and double-check that the latitude and longitude coordinates are correct. We can also set waypoints in a chart plotter by using the cursor position, and we'll look at that shortly. You should avoid placing waypoints directly on navigational aids or charted features. The accuracy of GPS is such that you stand a very good chance of navigating directly to that position, which could result in what is known as a plotter-assisted collision with the features. In this instance, we have plotted a waypoint on our chart just south of the green lateral buoy off Huckle Head. We read the latitude and longitude coordinates of this position from our chart, and they are 46 degrees 11.412 minutes north and 005 degrees 54.360 minutes west. We then enter this into our GPS, being very careful to enter the correct digits. If we select the GPS Go To function to navigate towards that waypoint, it will display the bearing and distance to the waypoint from our current position, which we see is 238 degrees true and 1.28 miles. We could then use this to guide us as we navigate towards Huckle Head. When we're navigating towards a waypoint, it becomes known as the active waypoint. We could also plot our current position on the chart by using a bearing line from that waypoint towards our position, using the reciprocal bearing of 238 degrees, which would be 058 degrees. Then measure the distance of 1.28 miles from the waypoint and mark off our position on the chart. We'll look at bearing and distance to waypoint in more detail in just a moment. Whilst it can be useful to plot your position relative to waypoints, it's easy to make mistakes. On a chart plotter, waypoints are normally entered by placing the cursor at the desired waypoint position, whereas on a GPS receiver, waypoints are programmed in by entering the latitude and longitude coordinates, and it's extremely easy to make a mistake. Imagine, for example, you plotted a waypoint on the chart with the idea of using it to help you navigate safely south from Cape St. Vincent to Edenfield, inside Diamond Reef, in thick fog, but you either measure its longitude incorrectly or enter into your GPS incorrectly by just 1 minute. It's easily done, believe me. Then, if you were fixing your position by bearing and distance to waypoint, when you believed you were at position A, you would really be at position B and heading into danger. Of course, if you were navigating diligently, you would also be watching your depth sounder and should realize that there is something badly wrong. Or, if you also plotted your fix by latitude and longitude, you would find a discrepancy. But it's better not to get it wrong in the first place. When entering waypoints off a chart into your GPS, check, check, and check again. Alternatively, if you are perhaps at anchor or on a mooring, when you program in your waypoints, check that the bearing and distance to the waypoint measured by the GPS matches what you measure on the chart. If there is a difference, you have almost certainly measured or entered the waypoint's latitude or longitude incorrectly. However, if you're sure that you entered your coordinates correctly, it can then often be easier when you're underway to plot your position on the chart using a GPS bearing and distance rather than by latitude and longitude. You can do this with a waypoint that you are currently heading to, or you could enter the latitude-longitude position at the center of a nearby compass rose into your GPS. By setting the compass rose as an active waypoint, your GPS will constantly display the range and bearing to that point. You're not navigating towards that position, but you can plot your position relative to it at any time. Remember when you are plotting the position to read the bearing from the opposite side of the rose, as the bearing on your GPS is from you to the waypoint. So, for instance, in the first plot at 10 o'clock, the bearing to the waypoint at the compass rose is 310 degrees. We plot the reciprocal bearing, which is 130 degrees, from the center of the rose down towards our position. And then plot the distance from the center, not the edge, of the rose. And try to set your waypoints where you can verify your arrival by other observations. Here, for instance, we could set a waypoint off Mutton Head in an arbitrary position east of the Mutton East Cardinal Buoy. A better option, however, would be to set the waypoint so that the Cardinal Buoy and the Mutton Head light are in transit at the same time as your track crosses the contour line. The radar's variable range marker could also be used to verify the fix at the waypoint. We will look at VRMs later in the course. When you're using waypoints to navigate towards, be aware that in busy areas, other vessels might be using the same or a similar waypoint, which could cause congestion at the waypoint arrival. A single waypoint may be used to navigate towards, or a series of waypoints can be positioned to mark successive legs on a route. But be very careful when building routes. In this instance, if waypoint 2 was mistakenly omitted from the plan, then the incorrect route would lead you into danger. As I highlighted a moment ago, when transferring waypoint positions from the paper chart to the GPS, there is potential for error, either by missing a single waypoint out or entering the wrong latitude and longitude coordinates. So plotting the route on your chart and checking the bearing and distance between each waypoint and comparing this against the GPS's calculated entries will identify any errors that may have crept in. If you're navigating towards a waypoint, your GPS can calculate all sorts of useful numbers based on bearing, course, and speed. These include course over the ground, COG, course made good, CMG, bearing to waypoint, BTW, and distance to waypoint, DTW. Some GPS units can also display heading, HDG, if they are interfaced with an electronic compass. Let's look at some of those terms now. Bearing to waypoint, BTW, can be extremely useful if you're sailing and beating to windward. You might plot two lines on your chart, perhaps 15 degrees either side, directly downwind of the waypoint, and keep yourself between them by monitoring BTW. In this case, we tack from starboard to port tack when BTW reaches 240 degrees, and back again when it reaches 210 degrees. By doing this, you not only ensure that you keep safely away from any dangers, but you also minimize the possible negative impact of a significant wind shift. And you can use course over the ground and bearing to waypoint to tell you when to tack in order to safely reach your objective. Here we are beating towards Fiddler's Race. Whilst we're on starboard tack, at point A, we record our course over the ground as 220 degrees, so we know that we can achieve that course on this tack. We then change to a port tack and wait until the BTW equals the recorded COG. At point B, we note that the bearing to waypoint is 230 degrees, so we cannot tack yet. But at point C, the BTW of 220 degrees equals the recorded COG on starboard tack, and we can now tack back towards the waypoint and clear the dangers at Hagg's Rocks with a safe margin. Your GPS can also give you distance made good, DMG, since you last activated Go To Waypoint, distance to waypoint, DTW, and cross-track error, XTE. We'll look at cross-track error in more detail in just a moment. And speed made good, SMG, speed over the ground, SOG, and velocity made good, VMG. Velocity made good, VMG, is a measure of your progress towards a waypoint. In this instance, port tack has a higher velocity made good than starboard tack. In theory, your GPS can also calculate how long it's going to take you to reach the waypoint. Depending upon the make of receiver, this will be displayed as either time to go, TTG, or estimated time of arrival, ETA. But it's only really meaningful if your COG is taking you directly to the waypoint, because it performs its calculation based on something known as velocity made good to waypoint, or VMG to waypoint, which is the speed at which you are approaching the waypoint at this instant. In this case, it would be 4.7 knots, giving a time to go of 2 hours and 8 minutes. But in reality, with a COG of 144 degrees and a BTW of 072 degrees, you're never going to get there without changing course. That said, racing navigators use VMG to waypoint a lot in order to determine which is the favored tack upwind or jibe downwind. Cross-track error, XTE, is the distance the vessel is to one side of the straightest line towards a waypoint, known as the rhumb line. In this example, if we failed to adjust our heading, you can see that the vessel would be pushed ever further away from the rhumb line by the force of the tide. The vessel's heading extension line is shown in red on the diagram, whereas the actual course over the ground is shown by the green extension line. Cross-track error can be displayed on your GPS as a distance and direction to get back to the rhumb line. Many GPS sets can also display this as a rolling road, which is a graphical portrayal of the cross-track error. The red mark on the GPS display is showing we are off track to port of the rhumb line, and the green arrow is indicating we should turn to starboard to return to that rhumb line. When you set a waypoint to navigate towards, the bearing to waypoint calculated by the GPS makes no account of any tidal stream that you may suffer. You might think it seems easy to just keep repeatedly altering course to steer towards your waypoint using the bearing to waypoint given by your GPS. But if you do that, you may be heading into danger. We can see here that the vessel is being set north by the tide, and as the heading is altered towards the waypoint, we will end up aground. The GPS will give no warning that your bearing to waypoint route will cross a hazard, nor will it navigate around the danger. However, the cross-track error displayed on the GPS would tell you that you are getting further away from the safe track that you had defined to the waypoint. The GPS display shown here is known as a rolling road, and we can see the cross-track error distance is given, and a green arrow is indicating that we need to turn to starboard to correct the error. Whereas, if you had adjusted your heading instead to maintain the cross-track error at 0, then you would be stemming the tide and would head more directly along the rhumb line to the waypoint and thus remain clear of the danger. So, beware of assuming the bearing to waypoint is the heading you should be steering, and always check on your chart to see what dangers might lie in your path. GPS does not allow for tidal streams, so always pre-plan the course to steer if there is likely to be a significant tidal set. And, as we saw in the lesson on tidal streams, if we fail to take account of the tidal stream on a longer passage and simply follow the bearing to waypoint on our GPS, then we will end up sailing further as the tide pushes us off our intended track. So you should plot a course to steer and monitor your cross-track error where tidal streams are likely to impact your passage. A cross-track error grid is a helpful tool for quickly plotting a GPS position on your chart as you navigate towards a waypoint. Here we have plotted one on our chart with 1 mile squares to help us navigate safely towards a waypoint positioned in transit with the leading lights into Whale Bay. With our GPS reading a cross-track error of 0.5 miles to port of our intended track, and a distance to waypoint of 3.5 miles, we can quickly plot a position on the grid, and we would know that we must turn to starboard to get back on track. Contrast this with what might appear a simpler alternative. Imagine it's dark and you're in a fast motorboat. The dashed line on this chart is your intended ground track from your 2100 fix to the waypoint at Whale Bay. You might be tempted to alter your course from your position at 2110 onto 110 degrees to head directly for the waypoint. If you did so, you might easily collide with the unlit yellow spherical buoy bang on your intended track. Not at all funny at 20 knots. If you regularly navigate into a harbour or estuary, and especially if you do so on a high-speed vessel, consider plotting a web of directions and distances like this on your chart. You can quickly plot a fix without using dividers or plotters. This method is particularly useful on fast-moving craft. You should also check your GPS accuracy from time to time. Sail or motor close to a fixed charted feature and compare the latitude and longitude reading on your GPS with the feature's charted position. Or plot the latitude and longitude position of your marina berth and see how your GPS position compares. You could also use soundings, transits, radar range and bearings, and any other relevant techniques to confirm your position. For example, a vessel travelling in the vicinity of Neptune Channel has set a GPS waypoint at the entrance to Fiddler's Race in position 45 degrees 46.79 minutes north, 5 degrees 43.80 minutes west. The bearing to the waypoint is given as 140 degrees true, and the distance to the waypoint is 2.63 nautical miles. If we carefully plot our position by range and bearing reference to the waypoint, we could then independently verify this by the following. The position lies on the 20-meter contour, so allowing for the height of tide, our depth sounder should confirm this. There are also numerous navigational aids for bearings. The cardinal marks on Jenner Island and Hagg's Rocks are fixed pillars, so will not be put out of position. And Beauty Bay Point Lighthouse and the radio mast south of the bay are both excellent bearing targets. As we'll see in the radar lesson, we could also use the radar's variable range marker to fix our position and verify the GPS data. And remember, if you are navigating by GPS, you should also keep a written log of your position, course, and log reading in the vessel's logbook. And plot your position on the chart at regular intervals, which for most skippers means once per hour. This will allow you to work out an estimated position if your electronic navigation equipment should fail. However, retrospective plotting of your GPS position means you will always be playing catch-up. For this reason, pilotage is often a more appropriate method of navigating in close proximity to any hazards. If you decide to let your autopilot take over, you should be aware that if you are currently off track to the active waypoint, it does not turn you onto a heading which matches your course over the ground, or even set your heading to match the bearing to waypoint, but turns you onto a heading which takes you back to the intended track as quickly as possible. This might mean a sharp 90-degree turn. So if you're confident that the run line from your position to the waypoint is safe, reset the cross-track error before asking your autopilot to navigate you to the waypoint. Not only can they navigate towards your waypoint, or keep you on a predefined course, but the autopilot can also keep the wind at a specific angle, enabling you to sail the boat efficiently, close hauled, upwind, or running downwind, without the risk of a jibe. They can also tack the boat for you and, as you saw on the last page, automatically track you to a waypoint. In fact, some are so good that they typically outperform a human helmsman, not only in terms of keeping a course, but also sailing the boat at the optimum angle to the wind, upwind. But make sure you don't just set your autopilot and become distracted. Imagine that you're heading to Namly Harbour and have programmed Namly Bar Beacon as a waypoint in your GPS. You set your autopilot to navigate to the waypoint, and then busy yourself with other things. What could possibly go wrong? Well, autopilots are very good at keeping you bang on track. So this means that if you fail to keep a good lookout, you will probably plough straight into Namly Bar Beacon. And it happens. A recent example of this was a new luxury motor yacht on sea trials with the proud new owner on board, along with a broker who was skipper and an engineer from the company who had supplied the instrument systems. The skipper asked the engineer to enter a major navigation buoy into the chart plotter as a waypoint. He then engaged the autopilot to navigate to the waypoint and started to explain the vessel's systems to her new owner. You can guess what happened next. As I said earlier, you should never place waypoints on charted features such as buoys. But also imagine there's some other vessel heading from Namly to Raw Marsh Marina. Ideally, you should plan your route such that you offset your course slightly to starboard of the run line. The next piece of equipment to consider is the chart plotter. And here you have three choices. A dedicated marine chart plotter display, often known as an MFD or multifunction display, a chart plotter program running on a PC, or a chart plotter app running on a tablet computer or smartphone. Each has its pros and cons. The purpose-built marine chart plotter is robust, waterproof, easy to read in strong sunlight, and intended for use in the harsh maritime environment. In fact, the chart plotter is usually a multifunction display and integrates seamlessly with other onboard electronics. You can overlay radar and split the screen to present data from any of the vessel's integrated electronic navigation equipment. An ideal setup is to have a master unit installed at the chart table and a repeater at the helm station. On the other hand, they are relatively expensive. You can't take them home to plan your passages, or take them with you if you decide to charter a boat in the Mediterranean for a change. They are often restricted to one publisher's charts, which are often more expensive than those offered for PCs and tablets, and updating charts may require additional hardware or new chart cartridges. A chart plotter program running on a laptop is a relatively cheap solution. You can buy a complete set of UK Hydrographic Office charts for the British Isles for as little as £20 and display them on a low-spec laptop using free applications such as Memory Map or OpenCPN software. Integrating GPS and AIS via readily available interfaces provides a fully functioning chart plotter. You can take it home to plan your passages, or with you if you charter abroad, and it can connect to the internet for chart updates. On the downside, they are fragile and virtually impossible to waterproof, and the screen can be impossible to read in strong sunlight or to dim sufficiently at night. A tablet or smartphone running a chart plotter app is a highly portable solution. Chart plotter apps such as Savvy Navi, CMAP, and IMRE Navigator are free to download with annual subscription charges required to access the chart area you wish to use. Charts are updated via the internet whenever they become available. Just make sure the device is fully charged before you need it. I can confirm that it's very disconcerting to see the screen go blank at the very moment you're approaching a tricky channel. Some are difficult to read in strong sunlight, and at the same time you can't turn the brightness down sufficiently to avoid compromising your night vision. Many manufacturers now make apps that enable wireless streaming between the chart plotter and your tablet or smartphone. This allows monitoring of the chart plotter data anywhere else on the vessel. For instance, on deck if a repeater display is not installed, or perhaps by the off-watch skipper in his bunk. You could also install an interface device that will make any of your vessel's navigation data available to your PC, iPad, or smartphone via a local Wi-Fi link. This allows your GPS, AIS, and instrument systems to transfer data wirelessly to your device, allowing compatible navigation apps to display and compute with real-time information. Incidentally, whilst your GPS receiver or chart plotter might only be capable of receiving Navstar GPS signals, modern smartphones will have an internal GNSS receiver and can obtain satellite-derived positions from all of the available satellite constellations. In this instance, we see that the phone has 9 GPS, 7 GLONASS, and 6 Galileo satellites visible to it. Your instructor's preference is a multifunction display interfaced directly into radar and AIS, of which more later, on the basis that it is the most functional, reliable, and easiest to use solution when the chips are down on a windy night in poor visibility with waves breaking over the boat. I would also always carry paper charts, of course. And I like to take a waterproof handheld GPS and a cheap notebook PC or smartphone equipped with a chart plotter app as a backup. Let's now look at electronic chart formats, of which there are 2 different types, called raster and vector. Raster charts are digital copies of paper charts. Therefore, they have exactly the same appearance to the equivalent paper chart. They are made up of a single layer of data, and there is no facility to filter the detail that is shown or to alter the visual presentation of the chart. As I said, they are exact copies of paper charts and will appear familiar in color and format to users of the equivalent paper charts. But remember, there are different publishers of raster charts, and digital versions will have the same differences as the paper version. Here we see both Admiralty and IMRE versions of raster and paper charts for the same area. Vector charts, on the other hand, are made from tracings of paper charts and use a database of features to build the chart display. This data is stored in layers and records every nautical chart feature, such as coastlines, buoys, lights, etc. These features and their attributes, such as position, color, size, shape, can be selectively displayed and interrogated by the user. Vector charts look different from familiar paper charts, but are more adaptable in use. On a raster chart, as you zoom in, you are in effect just magnifying the image. and as you continue to zoom in, eventually the image will appear pixelated. Whereas on a vector chart, the image remains clear as you zoom in and out. And chart details such as lights, place names, depths, etc. will be redrawn automatically to a different size to declutter the screen. These two screens are zoomed in by the same amount, and you can see the difference that the magnification has made to screen clarity. Actually, there's a bit of a misconception amongst some people that when zooming in and out on raster charts, that all you ever see is the same detail, bigger or smaller. If a larger scale chart is available of the area of interest, the display will automatically switch to that chart as you zoom in, just as you would pull out the same larger scale paper chart from your chart table drawer as required. As on a paper chart, the magenta boxes drawn on the chart indicate that a larger scale chart of that area is available. On the left-hand image, we see that an available larger scale chart is identified by the magenta border. And as we zoom in further, on the right-hand screen, the chart loads and the chart is redrawn to a larger scale. When the area covered by the large-scale chart is not fully displaying in the screen area, you can get a slightly confusing presentation, where part of the area is at a different scale to the other, as we see on the left-hand image. Zooming in further will fill the screen with the large-scale chart. We'll now look at the difference zooming in on a raster and a vector chart makes to the available information. Firstly, a raster chart. And now a vector chart. You can see that additional layers of information that would clutter the chart when zoomed out will only appear as you zoom in. In this case, we don't see the details of the precautionary area until the chart is sufficiently magnified. So it's important to zoom fully in and out to check for any important details. Vector charts allow you to turn various features on or off to declutter the screen, whereas raster charts are a single, fixed image that cannot be altered. So, if you're sailing in daylight, the layer depicting light features can be turned off, for example, and you could simplify the screen by removing the very deep sounding marks. But if we forget the chart is decluttered, we can come horribly unstuck. Forgetting that they were turned off yesterday can lead to disappointing tomorrows. In this example, we see the same vector chart side by side, with each set to display different levels of detail. The chart on the right is not displaying spot depths, buildings, place labels, light sectors, some navigational buoys, and prohibited areas. So, if you're using a chart plotter with vector charts, check to be sure you are satisfied with the level of detail being displayed. Whereas here, the zoom level on the chart on the left means that only one north cardinal mark is displayed. The chart on the right has been zoomed in further and now shows the other cardinal mark. A zoomed-out vector chart may result in some charted objects or hazards not showing, so it's important to zoom in to check if additional detail exists. If we compare this to the paper chart, we can see the full extent of this missing detail. A raster chart of the same area would display exactly the same information as the paper chart version, so those north cardinal marks would always be visible. So, to reiterate, a raster chart is a single layered digital copy of the paper chart, and there is no facility to filter the detail that is shown, and no detail is omitted at different zoom levels. The grounding of a Volvo Ocean race yacht, which ran into an Indian Ocean reef in 2017, provided a stark reminder of the need for caution when using vector charts. The reef was not depicted on the zoomed-out chart view that was being monitored by the professional navigator. The top chartlet shows the image shown as they ran aground, and the bottom image shows a zoomed-in view. What appears inconsequential at one zoom is clearly identified as a hazard further in. So, always make sure you zoom in sufficiently to interrogate the chart for all available information. Your chart plotter should be kept in the zoomed-in position to show as much detail as possible when navigating, and only zoomed out for passage planning or measuring distances. A split-screen display can be useful to show both detailed and overview charts side by side or different zoom levels. And it also enables a radar picture to be displayed at the same time as a chart, or a GPS rolling road view, or other vessel data. You can alter the unit settings on your chart plotter, and you should make sure that these match the settings of your paper chart. If we wanted to use this chart plotter in conjunction with RYA Training Chart 3, we should alter the distance setting to nautical miles instead of kilometers. Speed should be set to knots, and on this vector chart we could change the depth to meters instead of feet. Setting your chart plotter to display true bearings removes the need to apply variation when using course over the ground or other plotter-derived bearings in conjunction with a paper chart. Conversely, setting a plotter to magnetic bearings means that there is no adjustment needed when using a hand-bearing compass in conjunction with a chart plotter. Settings are, to some extent, a personal preference, but the key thing is to be consistent. Leaving the variation setting on automatic means that there is no requirement to update the value each year, or when the vessel travels to different locations. A chart plotter displaying vector charts will also allow you to change the coloration of the contours. On the left-hand screen, the safety contour is set to 2 meters to warn us of shallow areas that we want to avoid. So, anywhere with a depth of 2 meters or less at chart datum is colored dark blue, and on the right it's been set to 10 meters, which highlights the main shipping lanes which we might want to stay just outside of in poor visibility. If you're using a purpose-built leisure marine chart plotter, they are more likely to be using vector charts. Each chart plotter manufacturer has either developed its own range of charts or uses one of a very small number of electronic chart suppliers. Vector charts are created by companies such as Navionics, CMAP, and Garmin, amongst others. They are based on the National Hydrographic Office's data, but traced and compiled by their publisher. They are not subject to the same rigorous standards and quality control as those produced by National Hydrographic Offices, and it can, for example, be quite difficult to determine the source data. Vector chart publishers use their own color palette and symbology, and there are significant differences in presentation. Each of these chart apps are showing the same area in the Solent, and you can see that they have a very different look and feel. This is a rapidly evolving market, and chart publishers are continually incorporating new features into their chart products, including photographs, almanac information, satellite overlays, 3D views, augmented reality, and enhanced route planning. There are a few electronic chart terms and abbreviations that you need to be aware of. The term electronic chart can cover any electronic chart, but typically refers to unofficial charts, either vector or raster. These are usually published by commercial organizations and may not comply to any national or international standard. ENCs are electronic navigational charts. These are official vector charts produced to International Hydrographic Organization standards and issued by national hydrographic agencies. Raster navigational chart is an official raster chart which is an exact copy of official paper charts produced to International Hydrographic Organization standards. ECDIS, ECDIS, stands for Electronic Chart Display and Information System. This is the official navigational system approved for use by the International Maritime Organization. ECDIS uses official electronic navigational charts and meets the requirements for merchant regulations and is not something you will find on smaller vessels. To fulfill the backup arrangement requirements of the IMO, either a second independently powered ECDIS must also be fitted, or an appropriate folio of corrected up-to-date paper charts for the intended voyage must be carried. Only official electronic navigational charts that meet international standards can be referred to as ENC or RNC. All other charts are referred to simply as electronic charts and are mostly, but not exclusively, vector charts. Electronic charts made for the leisure market are not official navigational charts and are not considered to be suitable for use as a primary navigation source. For this reason, leisure chart plotters usually display a warning when they're switched on, requiring users to accept the limitations of the product. Official paper charts, sailing directions, pilot books, and notices to mariners should be used to verify the information displayed on electronic charts, and prudent navigators would always use an independent means of position verification. These symbols indicate the quality of data derived from the accuracy of the original survey and are displayed on official electronic navigational charts. However, it's important to note that chart plotters intended for the leisure market do not usually have the ability to display information about the quality or accuracy of the original survey, and the appropriate up-to-date paper chart should be consulted. The UKHO Quick Guide to ENC Symbols provides further information on this. When determining how much to rely upon an electronic chart as a primary navigation aid, you need to assess the following. How reliable is the chart? Is it an ENC, RNC, or electronic chart? Can I verify whether the chart is up to date? Can I verify the HDOP and quality of the GPS fix? Can I plot a position independently of a GPS fix? If you cannot positively answer all of these questions, the electronic chart is at best useful for situational awareness or rough planning. So, bearing all that in mind, let's see what your chart plotter can do for you. As we saw earlier, it can show your position, which is depicted by the black vessel icon on the screen and by the vessel position data box in the top left corner. You can either center the screen on your vessel or pan the screen to show more of the chart area that you're heading towards. On this chart plotter, the cursor position is being shown in the bottom right corner. A common mistake, which you should take care to avoid, is to use the latitude and longitude figure of the cursor when plotting your position. As well as your current position, the chart plotter can show your projected course over the ground. This is depicted by the green arrow here, which makes it clear if you are sailing into danger. If your chart plotter is connected to an electronic compass or heading sensor, it can also show your heading, depicted here by the red arrow. Without a heading sensor, the chart plotter will rely on a GPS-derived heading, which will be your course over the ground. These course over the ground or heading extension lines can be displayed as either time-based or infinite. Time-based extension lines provide a visual projection of where the vessel will travel within a fixed time period, subject to no changes in course, speed, tide, wind, etc. The extension line time period can be adjusted to your desired duration in the appropriate settings control panel. The purple lines represent our intended route, or run line, between the waypoints on the route that we have built, which we'll look at in just a moment. And the black dotted line represents the distance and bearing to the active waypoint, that is, the one that we are currently navigating towards. Waypoints are colored purple except the active waypoint, which is black. So you can see that Roselle SWM waypoint is purple, whereas range head is black, and that's the one that we are currently heading towards. The data box at the bottom of the screen is showing the bearing and distance to the active waypoint. So in this instance, the navigator has turned towards the range head waypoint before first arriving at the Roselle SWM waypoint. In fact, there's no good reason for setting the Roselle waypoint so far out. We can see from the black dotted line that this route doesn't carry the vessel into any danger, so the Roselle waypoint could quite safely have been moved closer in to that safe water mark next to the vessel's current position, which would also have served as confirmation of our arrival at the Roselle waypoint. We can set various alarms on the chart plotter, including depth thresholds, waypoint arrival, and cross-track error. When setting waypoint arrival alarms, it can be beneficial to set a large alarm radius, if you're following a route in open water, to allow for greater flexibility when executing the passage. And setting larger cross-track error alarms may be better on routes where there are no hazards or where cross-track error will vary with the effect of changing cross tides. Whereas a smaller cross-track error alarm should be set when deviation from the planned route is required to avoid navigational hazards. When using a vector chart, you can place the cursor over charted features and interrogate the underlying database to reveal more information. Here we see that we have placed the cursor over the range head south cardinal mark, and the information box that appears contains the relevant details. Let's just reiterate those lines and symbol colors. It's important to understand, however, that lines and icons may be represented differently on different manufacturers' chart plotters, and they can also be customized by the user in some instances. We can easily enter a new waypoint on our chart plotter, either at our current vessel position, wherever we place the cursor, or by entering it as a latitude and longitude position. Entering a waypoint by hovering the cursor over our intended waypoint position is obviously much easier than entering in the latitude and longitude of that position, and avoids any input errors. Plotting waypoints and building routes is as easy as placing the cursor where you want the waypoints and pressing Enter for each point on your intended route. However, as I said earlier, use good judgment when placing your waypoints to allow you to verify their position by other means. Here, for instance, it would be better to move waypoint 4 so that it's out of the main channel, but still within the small boat channel, slightly to the west and in line with the charted transit of the church spire and radio mast. And waypoint 5 should be moved to stay on that transit and placed at the point where it crosses the 5-meter contour line. And when you're entering waypoints, it's better to give them relevant names rather than just allowing the system to allocate numerical labels. This will help prevent confusion as you navigate along your route and also make it easier to retrieve a stored waypoint for future use. Take a look at this final waypoint on the route towards Stevenstown. Can you think how we could improve its position? It would be better to move the final waypoint to allow you to use a transit on the breakwater lights on your approach. This new position sits on the contour line, so you can verify your arrival. Remember to add the height of tide at your arrival time. As we noted earlier, the key point is to avoid arbitrarily placing waypoints and look for ways to verify your position. Many chart plotters also incorporate an auto-route function, but you should use this with extreme caution. Once you've entered the vessel's safe depth and perhaps air draft and beam, and specified the final destination, the chart plotter will build a route and insert suggested waypoints. The red warning symbol alerts the user to some potential physical hazards that the chart plotter has identified along the route. For example, shallow areas, air clearances, or if a route passes too close to an obstacle. On most chart plotters, you can access more detail about the warning in a pop-up information box. Autoroute should only ever be used as a first step, and should never be relied upon without close scrutiny of the full suggested route. Each section should be checked and modified to ensure that a suitable and safe route is in place, whether a warning is displayed or not. And you should be aware that the autoroute function does not take account of wind or tide. You can click on any of the waypoints inserted by the autoroute function and move them further away from any hazards, or into a position where your arrival at the waypoint can be verified either by using electronic aids to navigation, such as depth and radar, or by visual navigation. We see here that the warning triangles are indicating proximity to shallow areas at the start of the route, and to the rocks south of the safe watermark at waypoint 8. You should also consult the relevant pilot books for any restrictions or regulations that the autoroute function may not have included in the proposed route. Here, for instance, we see that the pilotage notes for Port Fitzroy on page 88 of the Training Almanac indicate that we should plan our route to exit between number 10 and number 8 port hand lateral marks, and that the autoroute function has disregarded this. Additionally, waypoint 8 has been set in proximity to the safe watermark, which is specifically discouraged. So we should add another waypoint to exit between number 10 and number 8 port hand lateral marks, and move waypoint 8 south, close to the final port lateral mark. This area will be less congested, and we can confirm our arrival at the waypoint by proximity or bearing to the channel mark, and also by the depth as we cross the contour line. As this route goes through some shallow areas, a minimum depth alarm would be helpful. Automatic Identification System, or AIS, which we will look at in more detail shortly, and VHF port control on channel 7.4 should also be monitored to provide a picture of traffic movements in the busy commercial harbour and approaches. The route after waypoint 9 would take the vessel through the overfalls off Tintagel Island and close to the unmarked rocks. Moving this waypoint to avoid these hazards would be better, and preferably to a location that could be confirmed by radar range off the surrounding islands. With the strong tidal flow in the Fiddler's Race, a small cross-track error is important, and this should be closely monitored, especially as you approach the Needle and Tintagel Island. A radar range would also help to confirm your position and ensure you are not being swept north by the tide as you approach the waypoint. A radar range is used in navigation and pilotage to identify the distance from your vessel to a target object, such as a prominent geographical feature or navigational object. We'll look at radar ranges in detail in the radar lesson. And waypoint 10 could be moved further off the headland to clear the tidal overfalls and off-lying rocks. Setting the waypoint on the 30-metre contour would allow you to confirm your arrival as you reach this depth plus height of tide. A radar range set on Beauty Point would give additional reassurance that you are a suitable distance off. Waypoint 11 would be better sighted to the north, so that it's clear of the 10-metre contour and lies on the charted transit. A new waypoint, 11B, could be placed where the leading lights intersect to give confirmation of the turning point. Waypoint 12 should be moved so that it lies on the approach line indicated by the moire effect light mounted on the bridge. So as you can see, you need to be sure that waypoints selected by the autoroute function are in sensible places, and if necessary, refine their position, such that your arrival at the waypoint can be verified either by electronic aids to navigation or by visual pilotage. And you need to identify and monitor hazards along the route and utilize suitable mitigations. If you're not using the autoroute function and set a single waypoint to navigate towards a destination, and then select that as the active waypoint using the chart plotter's Go-To function, this will display the shortest route between your starting point and the waypoint, the RUM line. It does not take into account any obstructions or hazards between the vessel's position and the waypoint. The ground track shown in this screen, for instance, passes across land and through a restricted area. It will be better to use pilotage to get out of Port Fraser, then ensure that there are no hazards along the route before starting the Go-To function once clear of the channel. Once the Go-To function has been activated, as well as the range and bearing to the active waypoint, the chart plotter will calculate the estimated time of arrival, abbreviated to ETA. This is based on the vessel's speed over the ground and total route distance. This should not be taken as an exact figure, as the vessel's speed and course over the ground will fluctuate throughout the passage. For this reason, an ETA is more likely to be accurate over shorter distances. As I said earlier, it's important to avoid over-reliance on electronic aids to navigation and to independently verify the displayed position. This should be done by means of visual fixes, soundings, transits, clearing bearings, dipping distances, and any other available means. Here, for example, the vessel's position is supported by the depth reading, but bearing to waypoint and distance to waypoint are both GPS-derived, so do not provide any additional verification. Visual verification of the light sequences of the various lit marks, details of which can be found by interrogating the chart plotter, will further verify the position. If the chart plotter stops receiving position data from the GPS, it will display a warning message. Just as with the standalone GPS receiver, the reason for losing position data could be antenna failure or something inhibiting the antenna, such as coils of rope or somebody sitting against it, failure of a cable or connection point between the antenna and the chart plotter, a poorly mounted antenna or the use of an internal rather than external antenna, an interruption to the satellite system or poor satellite coverage. And here we see that the GPS position fix has been lost. Therefore, the displayed position is unlikely to be accurate and caution is required. Options for a visual fix would seem to be limited, although further features and/or hazards may be shown on the chart when zoomed in or by referring to a paper chart. Depth, boat speed, trip, derived from the water speed log reading, and heading data are still available, so a DR or EP from the last known position would be possible. There will be an area of uncertainty on this position until additional verification can be made at the earliest opportunity. Chart plotters can also show tidal stream predictions now and in the future. And tidal heights in real time and predictions for standard and secondary ports. Chart plotters have a man overboard function, which is activated by pressing the MOB button. Take time to identify this on your chart plotter if you have one. Pressing the MOB button on your chart plotter should be an immediate action by the person closest to the chart plotter in the event of a man overboard, and everyone aboard should know how to operate this function before setting off on any passage. The chart plotter will record the latitude and longitude position at the time the MOB button is pressed, and mark that position with an MOB icon. It will cancel any active waypoint, and instead show the range and bearing to the position that was marked when the MOB button was pressed, enabling you to navigate back to that point and recover the casualty. If the person overboard is wearing an AIS MOB device, this will show their position on your chart plotter, if it is equipped to receive AIS data. We'll look at AIS, which stands for Automatic Identification System, in more detail in just a moment. Once activated, the beacon will transmit its ID and position on a VHF channel reserved for AIS. Any vessel with an AIS receiver will translate this transmission into a position, range, and bearing, which may then be displayed on the receiver or a compatible chart plotter. The AIS MOB marker is a red circle with a cross. The AIS marker is based on the GPS location of the beacon itself. Its position will be updated to reflect the changing position of the casualty over time, unlike the MOB waypoint, which will reflect the position at the time the button was pressed, although some plotters can apply the set and drift of the vessel to the original location of the MOB in order to update this position. AIS, or Automatic Identification System, is one of the maritime world's biggest technological developments in recent years. Vessels fitted with an AIS transceiver use VHF radio frequencies to automatically broadcast information about their position, course over the ground, speed, identity, type, and other safety-related information gathered from the vessel's GPS and other navigational input sources. This information can be received by any other vessel equipped with an AIS receiver, and the broadcast vessel's position is then displayed on the chart plotter or by other means. This data can then be used to assist in situational awareness and collision avoidance decision-making. AIS is primarily intended to allow ships to view marine traffic in their area and to be seen by that traffic. It's much simpler to use than radar for vessel identification and collision avoidance. However, it does not help with navigation and pilotage, unless AIS A2Ns are displayed. And we'll look at these shortly. Primary collision avoidance decisions should not be made based on using AIS alone, and there is currently no provision in the collision regulations for the use of AIS. See Marine Guidance Note 324 for more detail. There are, in fact, three types of AIS equipment: Class A, Class B, and Receive Only. Class A is intended for vessels where the fit is mandatory and transmits more information more frequently and at higher power than Class B. AIS uses VHF radio frequencies, and transmission from Class A transceivers can be received for 20+ miles in good conditions. As this requires line of sight, the height of each vessel's aerial will have a significant impact on reception range. Transmissions from Class B transceivers are much weaker and range up to only about 10 miles. Additionally, there are Class B receivers, which, as the name suggests, receive AIS data from other vessels but do not transmit a position or other information from your own vessel. The compulsory carriage requirements for AIS are covered in the SOLAS 5 regulations and requires the following vessels to be fitted with Class A AIS. All ships of 300 gross tonnage and upwards engaged on international voyages. Cargo ships of 500 gross tonnage and upwards not engaged on international voyages. Passenger ships irrespective of size, and fishing vessels over 15 meters in length. There is no requirement for small commercial vessels or leisure craft to carry AIS. However, should they choose to do so, they should be fitted with an AIS-B transponder or receiver. Class A vessels transmit every 2 to 10 seconds, depending on their speed, whereas Class B vessels are set to a nominal rate of every 30 seconds. However, it could be longer depending on speed and the amount of priority traffic in the area. Class B does not have priority transmission. If you have an AIS receiver installed and integrated with your chart plotter, vessels transmitting AIS data will appear as icons on your screen and automatically warn you if the closest point of approach CPA will come within an alarm threshold which you can determine. You can also see the predicted tracks of other vessels relative to you in order to assess whether you will pass ahead or astern of them. AIS targets marked as red, as seen in this example, represent a possible collision risk. Selecting a vessel's AIS icon with the cursor will bring up an information box with further vessel details, including the CPA and time to closest possible approach, TCPA. We see here that if neither vessel changed course or altered their speed, in 12 minutes' time they would pass within 0.12 nautical miles of each other. Most systems will allow you to enter your own CPA and TCPA values for when an alarm will be triggered. You need to decide how close you want to let other vessels get to you before an alarm sounds, and also how much time you need to take avoiding action. In this example, we have set the CPA zone to 1 nautical mile, and the time to closest point of approach, alarm, to 5 minutes. This means that when a vessel is detected to have a closest point of approach of 1 nautical mile or less, an alarm will sound 5 minutes before it reaches this point to alert you and give you time to take any action that may be required. Prudent use of the CPA and TCPA alarms will definitely make your voyages safer. But do familiarize yourself with how your particular system works, and know how to turn off the alarms when you are approaching busy harbor entrances and rivers. Otherwise, they will keep going off and drive you crazy. In this simulation, you can see that if both you and the dangerous AIS target maintain the current course and speed, you will not collide, but you will pass close ahead of the target. Perhaps not such a great idea if it's a large vessel navigating in a narrow channel. Make sure that you make appropriate judgments and do not simply rely on your AIS telling you that you will not hit each other. And here, as you make your approach to cross the Lawrence Channel TSS, you monitor the vessel Northern EPB on AIS as the vessel turns into the westbound traffic lane. The target vessel's rate of turn, ROT, is shown in the data box as 7 degrees per minute. The CPA and TCPA will continue to change until the vessel completes the turn and the COG and SOG become steady. Until then, the data shown cannot be used to assess the situation fully. So, be aware that AIS gives a snapshot of vessel traffic. You need to monitor the situation closely to take account of vessel movements and assess the information behind an icon to understand how reliable it is. Here are the basic AIS target symbols that would appear on your screen. Smaller triangle-shaped icons are most likely leisure craft, and larger box-shaped icons represent commercial vessels. A moving AIS target will have a line extending from the icon indicating the target vessel's course. Targets that are approaching you with a risk of collision are shown in red. Others are shown in blue. The AIS information panel also includes the target's name, call sign, and MMSI number. If the other vessel is the give-way vessel, and you're worried that they are not taking action to avoid a collision, you might consider calling them on your VHF to ask whether they have seen you and what maneuver they intend. Whilst the use of VHF for collision avoidance is discouraged for the reasons detailed here, placing a DSC call using the MMSI and opening a dialogue with the bridge of a ship can help to clarify a potential collision situation. But this should not be at the expense of taking any necessary avoiding action, which should be made strictly according to the collision regulations. Marine Guidance Note 324 contains the full guidance from the UK's Maritime and Coast Guard Agency. AIS has the potential to make a significant contribution to safety. However, AIS information should always be treated with caution, and do not over-rely on AIS for collision avoidance. It's very tempting to concentrate on the AIS targets on the screen and forget that it may not give a complete or correct picture of shipping traffic in your vicinity. Almost all commercial vessels will be fitted with AIS, but remember, there is no requirement for leisure craft to install AIS. AIS fitted on other vessels might be transmitting incorrect data due to input errors, which may in turn lead to misleading information being displayed. AIS positions derived from another vessel's GPS may not coincide with its exact position due to GPS errors. And even if they have AIS, they might not be transmitting, Under certain circumstances, AIS may be switched off at the master's discretion. Warships certainly have them, but almost always have their AIS transmitter turned off. Although I have heard the port traffic controller calling a warship on VHF to instruct them to turn their AIS system on in no uncertain terms. Fishing vessels over 15 meters in length are now equipped with AIS, but any number of vessels below the mandatory carriage requirements could sink you whilst scarcely noticing the impact. AIS information is available to all by direct reception with an AIS receiver. But you can also see AIS data for any area in the world on various internet sites, such as marinetraffic.com. These work by taking the data from a number of receiving points around the coast and aggregating it to give an overall picture. So if your family or friends are out sailing and have installed AIS, you can keep an eye on where they are. Here we see the very busy English Channel, and if we click on one of the vessel icons, a detail panel appears with specific vessel information. Web-based AIS apps rely on an internet connection and are not usually able to predict CPA or TCPA. They are also often subject to a time lag. Direct reception of AIS data is a more reliable setup. So, if you are using a smartphone or tablet to monitor AIS whilst on board, it's best to do so via a chart plotter repeater app, or by a Wi-Fi link to your onboard AIS if available, rather than a website or AIS app. As well as vessel identities and positions, AIS transmitters are increasingly being used to identify floating or fixed aid to navigations, A2Ns, such as a buoy, beacon, or light. Known as AIS A2Ns, they enable you to identify the mark even before it's close enough to be visible from a vessel or to provide a radar return. In this example, the Bramble Bank West cardinal mark is marked with an AIS A2N symbol in addition to the usual icon, denoting the buoy type. It's important to bear in mind that there may be a variance on AIS A2N information that will be displayed by different display manufacturers. And here's how that AIS A2N is depicted on the paper chart, with the magenta AIS text indicating its presence. AIS A2Ns are in fact classified into three types. Real AIS A2N, a physical aid to navigation structure on which an AIS transmitter is affixed and from which AIS messages are broadcast. Synthetic AIS A2N, a physical aid to navigation structure without an AIS transmitter, but for which AIS messages are broadcast from another, usually land-based, location, indicating the location of the structure. And virtual AIS A2N, an aid to navigation with no physical structure. It exists only through AIS messages broadcast from another location. A few uses of virtual A2Ns include environments where buoys are moved seasonally, such as in sea ice, or where a marker needs to be placed quickly, such as to mark a newly identified isolated danger or wreck. These aids can only be seen on ECDIS or other virtual AIS-enabled displays, such as a ship's radar. On paper charts, AIS A2Ns are indicated by a magenta circle surrounding the existing A2N symbol and an adjacent legend stating AIS. Virtual AIS A2Ns are indicated by the V-AIS text and magenta circle. On electronic charts, real A2Ns appear as a diamond with a cross at the reported position. If the A2N is off station, the diamond will be red. Virtual A2Ns have a V shape below the cross. Radar is of course a key aid in navigation, pilotage and collision avoidance, and we will look at this separately in the radar lesson. AIS should not be considered a replacement for radar, but it does have certain advantages. AIS uses VHF radio frequencies and can see targets that may be in radar blind spots. It's easier to use and interpret, and uses considerably less power than radar. However, radar can provide the range and bearing of physical features and charted objects. AIS cannot. AIS can only be used for position verification if AIS A2Ns, aids to navigation, are available and visible on your chart plotter. Radar can detect rain or squalls and provide direction and distance from the vessel's position, whilst AIS has no benefit in this regard. Both AIS and radar should detect nearby vessels, subject to generating a reasonable radar return or the vessel transmitting AIS data. AIS and radar can calculate CPA and identify dangerous targets, although neither system can account for future changes in speed or direction. In particular, AIS absolutely cannot be relied upon as a replacement for radar when navigating in poor visibility. Vessels without an AIS transceiver will not be displayed, whereas a radar will return a signal and allow you to track vessels in your vicinity. Practicing in clear weather and good visibility will enhance your familiarity and confidence with all of your electronic navigation aids. It will allow you to check the information visually, and any misinterpretations can be identified, and misleading appraisals which could be dangerous in restricted visibility can be rectified. Let's summarize some key points. Keep a written record of your position, course, and log reading in the vessel's logbook, and plot your position on the chart at regular intervals. GPS does not allow for tidal streams. Therefore, bearing to waypoint is not the same as course to steer. Following the bearing to waypoint may mean you are heading into danger. Check the cross-track error and plot your position. Try to set your waypoints where you can verify your arrival by other observations. Raster charts are copies of paper charts and cannot be modified. Vector charts are made up of layers of detail that you can turn on or off to declutter the screen. A zoomed-out vector chart may result in some charted objects or hazards not showing, so it's important to zoom in to check if additional details exist. Not all vessels will show up on AIS, and it should not be relied on entirely when assessing collision risks. Radar is a better tool for making this assessment. Here's a reminder of some of the abbreviated terms you will encounter when using electronic navigation aids. And finally, remember that GPS, AIS, and radar are aids to navigation. They should be used in conjunction with traditional navigation methods and a good visual lookout. In a pilotage situation, when navigating down a narrow channel, a carefully chosen transit will beat GPS every time. It's all too easy to be fixated by the vessel icon traveling across your chart plotter screen, instead of watching what's actually happening. Spending too much time at the chart plotter is a common trait of inexperienced skippers. Well done! You've completed the lesson on electronic navigation aids. Now attempt exercise G.